Welcome back to Philosophy of Mind. Before getting to the imitation game, I want to explain some background concepts to answer the question, can machines think? In order to answer the question of machine consciousness, we need to think very carefully about exactly what it is for our minds to be what they are. Around the time that Turing was writing, a new way of thinking about the mind was just taking hold, known as the computational theory of mind. And that is that the mind is a computer program that's run on the hardware of the brain. And the idea is that the mind functions by manipulating symbols according to rules, so-called laws of thought. So the way that your computer operates is that it has rules, like if-then sorts of processes. Get this kind of input, then you do this kind of thing. Symbols get input and they produce a certain kind of output based on the if-then sorts of rules. And the idea for a computational theory is that the mind works the same sort of way. We get sensory stimuli and the brain is organized according to rules that tell it what to do with the kind of stimulus that you get and what kind of output should happen relative to that input. So you've got these so-called laws of thought that operate on this incoming symbol system. And there's a complicated argument in the reading about whether humans follow such laws. This is objection 8 on page 65. And it's worth thinking about whether we actually do have laws of thought. Do we operate according to rules? Is that how thinking works? Or are there other ways to think about what thinking is? And Turing thinks that his ultimate answer to that is that there are certain kinds of laws of behavior, like if you're hungry, then you'll go eat. If you desire something, you'll go get it. These are the kinds of laws of thought that he had in mind and other computational theorists have in mind when they think about the rules that the mind operates on. But it's worth thinking about whether you think that that's really the case. We're not going to spend a lot of time on the question of laws of thought. That's more a general question of how the mind operates, and it's less specific to consciousness. But think about that in relation to the connectionist theory that we'll be talking about, and in terms generally about what you think a mind is. So in the computational theory, there are these laws of thought, and these functional relations, the relations that form the laws of thought, can be realized in a mechanical device by means of switches with two states, on and off. And that's known as a Turing machine. So your computer functions by these various different rules that operate, and there are switches, binary systems, zeros and ones, that are on and off switches. And the argument is that any system that's functional, that has these laws, that has these algorithmic operations, could be instantiated in a Turing machine. This is known as the Church-Turing thesis. Turing came up with this, and fellow mathematician Alonzo Church also proved that any computational function, that is to say any rules operating on symbols, is realizable in a Turing machine. So anytime you have any kind of system that is a system of rules and that operates on symbols, then you can realize that. You can make a computer with ones and zeros that can realize that system. So if the mind is computational, if the mind is something that is a matter of algorithmic rules that operate on symbols, then it can be instantiated in a computer. Now, it's going to take a while to come up with the right computer program, but the idea is that eventually we could figure out what that would be. So that's the Church-Turing thesis. That's the idea of a Turing machine. Here's an image of how, an example of how the Turing machine works. You've got a reader that says now in state 55, and it's reading a 1. And the rule might be if it's 55, if you're in state 55, then write a 0 and go to state 43. All right, and so then the machine would overwrite the 0 with a 1 and go to site 43, and then various different things would happen. For a more simple and familiar example of how this input-output sort of system works, when you type an A on your keyboard, then there's a rule system that says put an A on your Word document. Similarly, when you're printing it out, if there is this symbol of A on your Word document, then send this particular picture to the printer, and then it prints out a picture of an A. So these are the input-output relations that are operating when you use your computer to type a Word document. And the idea is that any Turing machine operates on similar sorts of systems of inputs and outputs. Now, an alternative to thinking about the mind as a computational system is known as a connectionist system. A connectionist theory of the mind suggests that what it is to be a mind is more like being a brain. And so the connectionist AI system then instantiates what the mind is in a different sort of program. And the idea here is that parallel distributed electrical processes of the computer program model neural processes through training of input and output relations. So instead of rules that operate on symbols, you have simply electrical relations that operate based on input, output, and training. So how this works is that you input various stimuli, like pictures of apples and oranges, into the bottom layer. You have the three layers. The input layer is at the bottom, and the output layer is the top. And inside there's a layer of hidden units. And here is a set of hidden units. There might be several layers of hidden units, and they might be related in various different ways. But this is a basic, simple, what they call feed-forward connectionist system. And the idea is that you feed the stimulus in through the input at the bottom, and the hidden units are in the very beginning randomized. They're randomized weights, and so you'll get a randomized output of the system when you feed in an input. If everything past that is random, then you'll get a random output, and it'll either be correct or incorrect. So if you feed in apple and it spits out orange, if we've got three output units up there, but let's just say it's two for the sake of simplicity. So you feed in an apple and it spits out orange, that's wrong. And so there's what's known as a back propagation algorithm. And you don't have to know that term, but the idea is that there's a algorithm, there's a rule that then reweights the hidden units to appropriately recalibrate the system based on whether the output was correct or incorrect. And over the course of time, you feed in lots of apples, you feed in lots of oranges, that is to say orange pixels of apples and oranges, and the output is either correct or incorrect either time. The system eventually learns. The weights become trained, as they say, so that when you put in a picture of apple, you'll get only the apple output. When you put in a picture of orange, you'll get only the orange output. And you can put in new pictures that the system has not been trained on, and it will distinguish apples and oranges based on the training that the system has gone through. And this connectionist system now is used in a variety of ways. Anytime you hear that a system is trained, it's probably using a connectionist sort of processing. Facial recognition algorithms are usually connectionist, I think almost entirely connectionist-based systems. So you have rule-based system, a computational theory of mind, and you have connectionist-based systems, which are connectionist theories of mind. And these are two alternative ways to think about how the mind works and to think about how AI works, about how machines might work or should work. So think about the difference here. And connectionists want to say that the problem with the rule-based program is that it's only simulating intelligence, that it's not itself intelligent. The computer is not itself intelligent. It's just got the rules in it that make it operate in the way that humans operate because it's been programmed by humans, but it itself doesn't learn, whereas the connectionist would argue that a connectionist system does learn, that it learns by interacting with the world. So this is one of the differences between the computational system and the connectionist system in terms of how it operates in the world. So you can think about which sort of theory of mind makes the most sense to you. One way to try to think about the question, can machines think, is to think about what it would take to prove that a machine is thinking. And Turing thought the way to prove it was to pass the Turing Test. And the Turing Test is based on a game played at the time called the Imitation Game. And there's a movie about Turing called The Imitation Game that I would totally recommend. It's a wonderful movie. It gives you a sense of the person and of some of the issues at the time, at the wartime, and it gives a poignant perspective on the question of the imitation game, on what's going on in the imitation game. So the way the imitation game works, it's a parlor game played with men and women, and you had the men and women, one man and one woman go in back rooms, and they needed to try to convince the audience that they were the woman. And so the man would say things that he thought a woman would say in answer to the question, and the woman would answer truthfully about how a woman would answer the question. And then the contestants would try to guess which one was really the woman in this game. And so Turing set up the similar sort of thing with computers, and he had a computer in one booth and a human in the other booth, and both interfacing, as the picture shows, through a computer, through, the person who was the judge would send questions to the one person and to the other person, and one of them would be the computer. And so you'd send a question to A, and you'd say, what is it like to be you? And A would respond back, I'm experiencing all of these sounds and sights, and it's I'm a little bored. And you would send the same question to B, and you would get a very similar answer. And you'd have to try to figure out, as the judge, which one's the computer and which one's the person. And so to pass the Turing test on this way of thinking about what the mind is for the judge to be confused, to think that either, I can't tell at all between, which one is the person and which one is the computer, or to make a mistake, to think that B is the person when actually B is the computer. Right? So this is the Turing test, and this is how it's played. And there's been a contest every year, and a prize given if you win. And the prize has been given out to people who did the best for many years. No one successfully passed the Turing test. There's some debate about whether there's a chatbot that passes the test. I went looking for this chatbot, and it's not available. The brief comments that are there say that it's not convincing that it's an actual person, but it did convince some judges that it was a person. But think for yourself about whether that is a sufficient test for a computer to pass. That if you can convince someone that if a computer program can convince a judge that it is a person, does that make it a person? And you might think back to the imitation game. If the man convinces the players that he's the woman, does that make him a woman? No, it doesn't. So if a computer convinces you that it's a person, does that make it a person? Arguably not. But if you're thinking that the computational theory of a mind is what it is to be a mind, that may be fundamentally different from being male or female, where convincing someone that you're male or female doesn't make you male or female. Maybe processing symbols according to rules is the only thing that it is to be a mind, in which case, if a computer is processing the symbols adequately enough so that the input and output relations are convincing, then maybe that is sufficient to be a mind. That's the question in the imitation game, and the question for you to think about. Does passing, or in the Turing test, does passing the Turing test constitute having a mind, or is it simply just simulating a mind?